Hello guys, nice to see you. How are you doing?
Hello.
Hi.
Good afternoon.
Hello. Okay. Good afternoon, everyone. So, as you already know, tomorrow we will have our first midterm, and you received a letter from me with detailed information on it. So, be ready. Take care that you need good internet access, reliable, and log in into Long Kappa at least 20 minutes before the start of the midterm to avoid some possible technical issues. Take your time to read all problems first. Don't read just one and start to solve it. Read all problems and decide which problems you can solve fast. Start solving them. Once you are done, then you can proceed and focus on other problems which are not so clear for you. Because if you spend all your time trying to solve some difficult problem, that may not let you and provide you enough time to solve those problems which are easier. And people with such approach may lose points even with some very simple problems. So please read all problems at once, think for a minute about them, and define your priorities in terms of the order how you will try to solve them. Keep in mind that your answer format should be according to Long Kappa rules. Otherwise, your answer will not be accepted. And other from that, just read carefully problems, try to think about them. Don't be too much in a rush when you read problems, because you need to understand what exactly is required from you. So hopefully everything will be good and you will manage to succeed with this first midterm. Also, my advice would be to look, maybe repeat a bit basics of derivatives, integration, maybe some simple differential equations, which are very simple in terms of solving, like spreading variables and having two integrals from both sides of the equation and just integrate them. So very basic knowledge would be sufficient, but be aware that there is a chance you will need to do something like that. So better keep some tables of different derivatives and integrals somewhere close to you, so you don't need to spend time looking for them.
I'm sorry, I have a question.
Yes.
About tomorrow's midterm. So how it will be conducted? There will be some kind of number of problems, and each problem will worth 1 point, or problems can worth more than 1 point, and we can accumulate more points than problems. And for example, will we be required to write the solution or it will be only answer?
No, you will submit only answer, and each problem provides like 1 point, but it doesn't matter so much what problem provides, because in any way overall performance will be evaluated, and that of course will be mapped to some average of your performance. Yeah, hello, who has just joined to us. Nice to see you guys. That's why don't worry too much about this. Just try to do your best in terms of solving as many problems correctly as possible, because obviously there will be different complexity of those problems. But your goal is just to solve as many, like submit as many correct answers as possible.
How many problems are there going to be?
I guess it was mentioned in the letter. I think this time it will be 6 problems. You will have 45 minutes for that.
Oh, okay. Sorry, I didn't notice. Thank you.
So yeah, problems cannot be like all problems too easy, you understand, because you need to have an option to have some like decent opportunities for evaluation of students' performance. Students perform in a different way, many students, and that's why we need to provide different types of problems with different level of complexity in order to give a chance for different students to show their knowledge of these topics and reveal their performance.
Will the difficulty of the task be comparable to those that we've solved on Long Kappa beforehand?
Yeah, there will be some, let's say on average, yes, but there could be that there will be 1 or 2 easier than average of your homework, and also 1 or 2 a bit more difficult than those in homework. It just, it definitely will be not the same complexity of each problem. And that's why my advice to you, please take some time at the beginning and read all problems, because even so, let's say there is a chance that you practiced while preparing for the exam, you solved some problem which is similar to that one, which is considered to be more difficult among these 6 problems. So if you have experience solving this type of problems, it will not be a problem for you to solve it in a very short time. So probably if you see it, so you can pick it up, put in the top priority at the beginning to solve first. So you are done with this, and the rest of the time you can dedicate to those problems which are not so obvious for you how to solve. So that could really help you not to lose those points, which you definitely can get. Unfortunately, it happens that, let's say, if there are like 3 problems which are quite simple, and I'm quite sure that 99% of our students could have solved it, somehow, sometimes average could be lower than 3. Means that on average, students didn't manage to solve all these 3 simple problems. And the reason for that, from my understanding, is just only mismanaging of their time, because they just start to solve problems as they appear, and they are randomly distributed. So they just spend most of the time for 2 first problems and don't have enough time to solve others, among which are very simple, which they would for sure solve. And it is still a big question if those 2 problems, which could be difficult at the beginning, and they kind of submitted the answers to them, if they solve them correctly. So it's a question. But with simple problems, you could be much more confident in your right solution. So that's why read all of them and range them by complexity. So start from easy, go to difficult. That will definitely help you to perform better on average. Okay, guys, so I think we can continue now with our discussion. If I'm not mistaken, we finished last time with mentioning about this internal energy. So we considered kinetic and potential energy, and mentioned that there is also another type of energy which should be taken into account, and that is particularly important when, for instance, we have some friction forces. So these friction forces convert kinetic energy, for instance, in heat, and we need to take into account this dissipation of energy because of converting kinetic energy into internal energy. So let us consider this a bit more in details. And also we will introduce today the concept of conservative and non-conservative forces. Okay, let me switch to slides. And so concept of internal energy. Let us consider some flat horizontal plane, and some body which is moving on this horizontal flat plane, and let's say it has some initial velocity v naught. So it moves along some trajectory on the surface, sliding on the surface, and stops at some point on this surface. So here v is equal to 0. Since, as we defined initially, this plane is horizontal, we don't change the height of this body, and means we don't change potential energy. And this initial kinetic energy, mv naught squared divided by 2, is converted in some form of energy, which is different from potential energy. And we need to take into account that there is some kinetic friction coefficient, which describes the interaction between the surface of the body and the plane surface. And obviously on this path, the body performs on the surface of the plane. There will be some kinetic friction force, which eventually the result of its of this force will be just conversion of kinetic energy into internal energy, means just in heat. So it will be E internal energy. So we take this into account when we have a complete situation of conservation of energy. So we need to take into account kinetic plus potential plus internal energy, and this should be constant. So with such approach, we can proceed further, considering some examples, which we will definitely do right after introducing the concepts of conservative and non-conservative forces. Afterward, we will just go through different situations with application of this law of conservation of energy. So conservative, let's start from conservative force. The definition of conservative force, there will be two requirements to fulfill this statement of a force to be conservative. Let us consider x, y system of coordinates. And here are 2 points, A and B. So there are different options how we can move from point A to B. Let's say we can go with a straight line between these 2 points. This will be path 1. However, we can go in a different path, which is longer. Let's call it path 2. So the first requirement for conservative force, so if somebody is moving from point A to point B under the effect of influence of conservative force, then work done by this conservative force along path 1 should be equal to the work done along path 2. So technically, in other words, we can claim that work done by a conservative force should depend only on initial and final position of the body, regardless of the path, like its trajectory of its movement from one point to another. So only coordinates of initial and final points matter. Another requirement is that, for instance, we use some path 3 with which we come back from this point B back to point A. So we have kind of closed circle. We started from point A with this path number 2 moved to point B, and then with path number 3 came back to point A. So in this case, we can write the integral along this closed path. So it's shown as integral with this circle in the middle of the dot product of this conservative force to displacement vector should be equal to 0. Means that work done by a conservative force while moving body in a closed circle, so coming back to this original point where this motion started, will be equal to 0. Net work will be equal to 0. So these are two requirements for conservative forces in order to consider them as so. And let us consider two examples of, first example will be conservative force, another non-conservative. So let's start from conservative, and the best example for conservative force is the gravity force. So again, we have some system of coordinates. And so here are our unit vector, I unit vector, here's J unit vector. So we have some body. And imagine that it moves from coordinate y1 upwards to a point y2 with coordinate y2. So it can move upwards like shown here, or it can move with some other trajectory, doesn't matter. What really matters here is the initial and final position. So work done by gravity force, because here we have some mass, mg, of this body. Definitely in order to, when this body is moving, gravity force mg will perform some work. And in order to calculate it in this two-dimensional space, we need to get the scalar product of two vectors, which will be the gravity force itself times displacement. So this will look like this, work done by the gravity force. So minus mg times j. So here we have minus because it's pointed down in opposite direction to axis y. Dot product with a displacement vector, which will be y2 minus y1 times j. Yeah. So we have two vectors which have to be multiplied in scalar way. So we get a scalar number as a result, and it will be mg. And here, in order to take into account this minus, we have y1 minus y2. So we just flip these guys in parentheses. So we have the expression for work done by the gravity force. And now we see that it's only initial and final position matters in the work done. There is no evidence of any path or trajectory of this motion here in this equation. So that satisfies first condition for conservative force. And then if we substitute instead of y2, y1, so we write that y2 is equal to y1, means that we made a closed circle, then it will be equal to 0. And that will satisfy the second requirement for the definition of conservative force. Another example of non-conservative force is the friction force, which we already considered. So we have a body on a plane, and then there is some, so it moves with some velocity vector. It can move to a new point like this or like this. So again, it will be 1 and 2, pass 1 and pass 2. So obviously here will be some kinetic friction force pointed in the opposite direction to the velocity vector. So work done by moving this body from initial to final position along path 1 will be equal to the product of kinetic friction force times the length of this trajectory, means the path. So let's mark it as S1. So work done by moving this body along path number 2 will be equal to Fk times S2. Since S2 is larger than S1, W1 is not equal to W2. And that is already violation of this definition of conservative force. So now if we assume that from this point we move the body back to the initial point, so it has some trajectory number 3. Along this path 3 will be some work done. It will be equal to Fk times S3. And eventually, if we, like the total work which will be done by moving this body from initial point to this intermediate and back to initial, will be W, let's say 2 plus W3, and this is not equal to 0. So means that the work done in a closed trajectory by this kinetic friction force is not equal to 0, which is violation of the second requirement for definition of a conservative force. Means that friction force is a classical example of non-conservative force. So one more statement I would like to make here, that in the closed system, when we have something like body earth or body spring systems, the work done by conservative force causes decrease of the potential energy. So let us write it down here. So work done by internal conservative force inside this system, for instance, body earth, means internal conservative force is gravity force in this case. If it's system spring body, then this internal conservative force will be the spring force. Internal work by moving body from initial to final point. Here is some internal conservative force, which is a function of position, will be equal to minus delta U. So it this work of internal conservative force results in the reduction of the potential energy. Kind of makes sense if you think about it, because if we have some body at certain height, and then this body is falling down to another height, which is smaller, then some positive work is done by gravity force. By positive...
Excuse me.
Yes.
Excuse me, Professor. So why are you talking about potential energy while you're considering the movement on a horizontal surface?
Oh, no, but we are done with this. So it's example of non-conservative force, and that is friction force, which we consider on this horizontal surface. So we gave an example for conservative and non-conservative. Now we are done. And now the next step, when we deal with conservative force, so this force F as a function of X, we consider that it is conservative force. In this case, work done in a closed system by conservative force is always causes the reduction of potential energy. So it's kind of the statement which you should remember and understand. So it has nothing, this equation has nothing to do with this plane, horizontal plane, and friction force. Friction force is not conservative force. So is it clear?
Yes, thank you.
Okay, you're welcome. So this statement is important because we can express, so for instance, we can write that potential energy at a final position is equal to this minus work done by internal conservative force, moving from initial to final point, the object, plus some constant. And this constant is the initial potential energy, which could be arbitrarily set to 0 or to any value, because we can, with potential energy, we can arbitrarily set 0 level at any convenient level for us. So now we can take differential of this part, and it will be du. So in order to get rid of integral, will be minus f as a function of x dx. And from here, we see that the force, in this case, it is internal conservative force, F as a function of x, is equal to minus du over dx. So the force is defined, the conservative force is defined as the negative derivative of potential energy over displacement dx. So this is written for motion along a straight line, so one-dimensional case. If we have some multi-dimensional case, then we can write the following. So F vector of this conservative force can be represented as negative, like sum of negative derivatives of potential energy in different directions along 3 axes of coordinates. So it will be du over dx times I unit vector minus du over dy times j unit vector minus du over dz times k unit vector. So in other form, it can be written as minus gradient of scalar field u as a function of x, y, and z. Almost no space here. So this form of partial derivatives along different axes of coordinates is called gradient, is the direction of the fastest change of the scalar field defined in this space, which is potential energy in our case. So gradient of potential energy with the sign minus defines the conservative force vector. So this is the relationship between conservative force and potential energy of the system. If you have, for instance, potential energy distribution for different directions like x, y, z, you can take a gradient of this potential field, and it will give you the conservative force vector, which is...
I'm sorry, I have a question.
Yes.
Yeah, so you're saying that like potential energy can be distributed into more axes like x, y, and z axis, but potential energy is only dependent on height, isn't it? So
yes,
how...
so far you're totally right. So far, when we consider like gravity, so this equation is sufficient enough because we know that potential energy is changing only in one direction. However, there are other cases. For instance, potential energy of electrostatic field, and that could be distributed in 3 dimensions. Also, if we move like far away from the planet and consider planet as a point source of gravitational field, that could also result in 3-dimensional distribution of potential energy because it's related to the strength of the gravitational field, G. and that will have three-dimensional distribution in space. So it is what we considered up to now is some one possibility when we are close to the surface of the Earth, and then only the height from the ground level to the point where this body located matters in the definition of potential energy. However, in the broader understanding of this concept, potential energy can be a function of all three coordinates, and that is called potential energy field, which is defined in three-dimensional space, for instance, or in two-dimensional. So in our specific case, it is defined in one dimension.
And also, like, I didn't really get, like, how do we visualize here the force f of x and x itself? Like, x is what distance and f of x is what force?
Yeah, so let's say if we have f, force, and here x, some position in space. So if f is constant, then it doesn't depend on x and means that force doesn't change. However, f could be some function of x. So for each x, we can have different values of f. And then we write that f is a function of x, which we put here in this integral. And dx is just some small element of some interval on this axis x, which we tend to put to very small value in order to consider within this delta x constant force F at given x. And then we can divide this large area in many small intervals delta x and sum up the product of this delta x to this constant force F within this narrow delta x. And that is technically what is integration.
Yes, and we will find like work done, right?
Yeah, exactly. Because if we have a product of delta x, here small delta x to F, which is considered to be constant within this small delta x, it will be work done by this constant force F, like instantaneous value of this force when x is changing to small displacement delta x. So if we add all these small works done at each small interval from x1 to x2, then we will get the total work done by this variable force. And that is integral of fx times delta x.
And like work done not always converts into the potential energy, right? It can be like also converted into, for example, kinetic energy.
Sure, yes, but in case of the system, if we, for instance, consider some closed system, spring body, and it stays in equilibrium condition, so there is no like zero potential energy, then any work which we will do on the system will increase or decrease, depends. But let's say if it's spring in zero potential energy, like in ground state, then any work will increase the potential energy, means external work. But then if we release this external force, which push the system out of equilibrium condition, then the internal conservative force, which is spring force, will perform some work in order to put the system back into equilibrium condition. And that will, this work done by the internal conservative spring force will be resulting in the reduction of potential energy. Means that we will move this body from the excited state when, for instance, spring was compressed to initial position when the string was in normal condition without stretching or compressing. So work done by internal conservative force will always reduce the potential energy. Of course, while reducing potential energy, it will increase kinetic energy because this internal conservative force will accelerate the body. So it will start moving fast with some speed, means it will gain some kinetic energy. However, that is out of this discussion because here we focus on work done by conservative force and specifically potential energy, because then it gives us relationship between potential field, potential energy field, and conservative force vector. So once we have this potential energy field, by taking partial derivatives along each direction, we can calculate the internal conservative force. Okay, so let us then consider some example, maybe. So we have 5 minutes. Let us check what we can do for these 5 minutes. Let's say we have some surface with a spring attached to mass M1. Then it has some wheel and with massless and frictionless wheel and string, and not string, but some rope. It's attached to mass M2. So assume that it is fixed in equilibrium condition. So delta x of this string is equal to 0, means it's not stretched. So it's fixed, everything is okay. Now we get rid of this anchor and let this system to move to new equilibrium condition. Because of some weight mg, m2g, this block m2 will move downwards, so it will be somewhere here, new position. And obviously it will pull this block m1, so it will move to new position somewhere here, m1. This is m2. So the question will be what we want to know. What will be this distance? Let's call it h. The m2 and m1 blocks move in order to reach to new equilibrium condition, because obviously that this distance will be also h. This rope is not stretchable. So here we have interesting case of converting potential energy of one form, which is gravity potential energy, into a potential energy of another form, which is spring potential energy. So also what we should take into account that here is some kinetic friction coefficient. Means while this body M1, while it's moving to the right, there will be some force F, kinetic friction force, which will also dissipate some energy of this potential energy, gravitational potential energy. So we can write that change in the potential, gravitational potential energy should be equal to the change in the potential energy of the spring plus change in internal energy. So in this case, we can write that M2 times G times H will be equal. How do we define potential energy of the spring? Any ideas? Do you remember? We discussed that.
Yes, it's like K times delta. No, in this case
like
it's H
in this
squared.
case it's H.
Yeah, divided
H
by
squared
2.
divided by 2. Yes. And then we need to add change in internal energy. And how do we get change in internal energy?
It's just kinetic. No, not kinetic. Friction force times
friction
this.
Force.
Yeah, it's like Fk times H.
Yes, but Fk we need to define with via this mu k.
All right. So it will be like mg mu k times H.
Okay. So mu k times mg and times h. Yes? Like this. So this is reaction of the surface on the body M1. So this is M1. Okay, so now we can rearrange this. And from here, we can already express. So it depends what is unknown. So in this particular case, it could be different. It could be what is h? Then we have k h squared divided by 2 plus mu k m 1 times g times h minus m2 gh is equal to 0. So here we have a quadratic equation where h is unknown. So we can solve this quadratic equation. For instance, it could be that h is given, but mu k is unknown. So you can also express mu k from this equation. But the concept is that we need to take into account all forms of energy, like initial condition and final. Initial, we don't have any potential energy in the spring. And there is no work done by friction because body is not moving M1. So there is only potential energy of this body M2. But then this potential energy has changed, and that resulted in the accumulation of potential energy in the spring. And in addition, we got some work done by non-conservative force, kinetic friction force, Fk. Okay, so I think this is pretty much everything what we can do now, because we are running out of time. So please take responsibility and organize your internet connection in appropriate time slot. Be ready and focused on solving those problems and try to do your best. So good luck with your midterm exam tomorrow.
Thank you. Thank you.
Thank you. Goodbye.
Okay, bye. Have a good day. Take care.
Bye.